So check it out. In 6.1, you guys, you ready? In 6.1, all we were able to do was verify that a solution was a solution to a differential equation. We weren't able to actually find solutions unless we were already given a general solution. You guys following? Okay, 6.2 introduces one method of taking a differential equation and trying to find a general solution for it. Okay? It's called separation of variables. Separation of variables to solve a simple differential equation. Okay. Example. Now let's try this one more time. What would you call that kind of function? A differential equation. Okay. It's an equation, first of all, obviously because of the equal sign. And it's not just a normal equation because that's y prime. Y prime is a derivative, so this is a differential equation. Okay. It's important to recognize those. Differential equation. Okay. Let me show you what, or explain what the end result is. A solution to a differential equation is something y equals something. How can we go from y prime to just y? Integral. But the problem is we can't integrate 2x over y. You can't integrate when you have two different variables.
So are we going to do implicit integration?
Well, with differentiation, there was implicit differentiation. That worked, but that doesn't necessarily work with integration. So do you see the issue? If it was just y prime equals 2x, would this be a very hard differential equation to solve? Just integrate both sides, and you get x squared plus c. That would be really easy. Okay? But if it's 2x over y, you have to use this process called separate your variables. Okay? And it's not that hard. Okay? You ready? Multiply the y over.
Okay.
Now, notice we've gotten all the y's together on one side, we've gotten all the non-y's on the other side. Okay? Now we're going to integrate. So we're going to do the integral of y prime y dx equals the integral of 2x dx. Okay? The dx is there mostly to tell you what we're taking the integral with respect to. We're taking the integral with respect to x, not with respect to y. Okay? You guys ready? I want to consider this right here. Y prime dx is equal to dy. Why is that?
Oh my goodness, because it's a chain rule thing.
Isn't y prime just another way of saying dy dx?
So
So just multiply the dx over here and you get y prime dx is equal to dy. Do you see where that came from?
yeah.
Okay. So the next thing is to make a substitution, because what I was saying earlier, you cannot integrate if you have mixed variables. Here we have a y, but we're taking the derivative with respect to x. You see how that's a problem? So we're going to replace y prime dx with dy.
So it can be y dy.
So it's going to be y dy. The integral of y dy is equal to the integral of 2x dx. Now on the left side, we're not mixing variables. We're taking the integral with respect to y.
So it's just y squared.
So it's y squared over 2 is equal to x squared plus c. When you take an integral, you have to increase the power. Okay. And just multiply the other side by 2. Or multiply both sides by 2. So we're going to get y squared equals 2x squared plus c. Yes and no. Because what is c? And what's 2 times c? Still a constant, so it doesn't really matter. Does that make sense?
Yeah.
It's still a constant. Okay?
Yeah.
There's your solution. That's all you gotta do. Because how do you know once you found the solution? There's no more y prime. Is there any y prime in there?
Just red water.
So that's your solution. That's called separation of variables. Okay? The point is to get rid of y prime. We've gotten rid of y prime, so that's our solution. Let's just try a few of these. Another example. Use separation of variables. Well, if you need to use separation of variables, use it. Okay? Solve these. dy dx equals 6 minus x. And then dy dx is equal to 6 minus y.
He thinks he's so cool. No one likes Cade.
Guys are a bunch of jerks.
Cade sucks. Cade's a loser.
Oh.
How do you know I'm even recording?
Oh,
Am I recording? I better be.
I saw it.
You are.
I'm recording.
Cade sucks.
You should come to class.
Slupper.
What's the difference? You come to class and don't pay attention. Talk to Asa the whole time. Yeah! Sweet. Thank you, Connor.
Oh my goodness. Pay attention. Look at how full my notebook is. There's all these numbers and stuff in it.
Okay,
I got burned.
let's go on these two. Talk about it.
Easy. Because all you do is, well, 6 minus y, right? Dx.
Let's get to part B in just a second. I would assume you guys got somewhere on part A.
Yeah.
First thing you do is move the dx. Now, actually, let's do these at the same time so you can see the similarities and differences. If you move the dx over here on part B, okay, so check it out.
On part A, on the right side, you only have x's, right? And on the left side, you only have y's. That's a good thing. But here on part B, on the left side, you have a y, but the right side, you're mixed. You have y's and x's.
That's a problem, right? But on part A, we can just go right to integration. What's the integral of dy? Come on. It's just y.
Yes.
Integrate 6 minus x dx. You just integrate each individual piece. 6x minus.
Squared over 2.
Then you have your plus c. Okay? So the problem here is we can't just go right into integration because we have y's and we have dx's. That's not going to work when you're mixing variables. So what did we do in our first example?
So what if you kept it dy over dx and instead you you multiply the dx over that side, then you divided the 6 minus y from both sides, and you got dy over 6 minus y. Then you turn 6 minus y into 6 minus y to the negative 1 power. And
I get what he's going at. Oh, yeah.
actually then you'd be with 1 over 0.
Oh, you mean move this up and give it a negative 1 exponent?
Yeah.
Oh, okay. We could do that.
And then you get an
But let's go back to your first suggestion here. Okay, yes or no, this side only has y's.
Yes.
This side only has x's. So could we integrate from here?
Yeah.
I was thinking
Yes.
This has y's, this only has x's. So we could integrate straight from here.
Oh my gosh, that's what I did.
Okay. What's the integral of dx? Okay. I'm going to give you guys 1 minute here. I want you to think about this for a second. We've learned this. This, I hope, looks a little familiar. I want you to talk about it. I'm talking about this right here.
The absolute value and then ln of u, but you have to make
So, Braden, go ahead.
so
Hey, shut up.
the 6 it's a u prime over u, and so that turns into ln of the natural log. I mean, not the natural log. ln of the absolute value of u.
You guys follow?
Yeah.
Does this look familiar?
Yeah.
Yeah.
Does that look familiar?
Yes.
Does that resemble this?
Yeah.
Okay, we're missing something though. If we let u equals 6 minus y, then what's du?
Negative 1.
Negative 1 dy. So we gotta have a negative there and a negative there.
Yeah.
You guys with me?
Yes.
We had to have a negative 1 dy. Yes.
Yeah.
I'd say so.
So then it's negative ln of 6 minus 4.
So it's negative natural log of 6 minus y is equal to x.
The absolute value of 6.
The integral of 1 over u du is natural log. Okay. I want to make sure we're clear on this before I move on. Any questions? Where'd the minus sign come from?
Oh my gosh, they just...
We had to get du here. Okay. Now, this next part,
Then you have to put it to a base of e. Right?
exactly. Let's divide by the negative first of all, though. So we've got
Yeah.
natural log of 6 minus y equals negative x. You're not going to want to leave a solution to a differential equation in logarithmic form. Luckily, you guys are very good at going back and forth between exponential and logarithmic form. If you use a base of e on both sides,
Yeah.
doesn't that just cancel a natural log?
Oh, yeah.
Easy.
Then this is 6 minus e.
So
to
it's
the
6
negative
minus y equals e.
y. That's it.
Well, we move the negative over here to this side.
I'm so proud of you. Congratulations.
Okay. And there you would have it. Now exponentiate both sides and put it in exponential form. Okay. This section has it's got some word problems. Just a few. Well, I guess that's relative. It's got a few. But there's ones you've seen before: growth and decay models. Growth and decay models. Okay, this phrase you guys really struggled with a couple months ago. Right, Hayden?
Yeah.
You guys are really struggling today. And it's unfortunate to those around you who actually are trying to listen. Not unfortunate, inconsiderate would be a better word. So consider it up. Be considerate of others. So rate of change is directly proportional. Does this phrase sound familiar to a test we had a few months ago?
Yes, x equals y.
This kind of a phrase, and perhaps it was my fault for not really preparing you well enough for it, but rate of change is directly proportional. You're going to see this phrase in some of your problems today. There's two types of proportionality. There's direct proportional. What was the other one? Indirect. Okay. This one's going to deal with direct proportional or directly proportional. Okay. The rate of change is directly proportional to. You would write it like this. First of all, what is a rate of change?
Derivative.
It's a derivative. Okay, so dy dt, because in these problems, it's changing with respect to time. So it's dy dt. Now, if it's directly proportional, try to think about the difference between directly proportional and indirectly. What was the difference? Directly proportional is straight up multiplication. K is just called the constant of proportionality. Just so we can bring it up, what would indirectly proportional have looked like?
Wouldn't be
K over y. You guys need to remember this. Directly proportional is multiplying. Okay. Indirect is dividing, and the constant of proportionality is just K. And that's what you solve for using an initial condition. K represents a constant. What have we usually put here for a constant?
C.
C. How did we solve for the value of C?
Particular.
We had to have initial conditions, right? This is pretty much the same thing. K is just a constant, and we solve for it using initial conditions. Follow? So how this applies to growth and decay? If y is a differentiable function of time or of t, such that y is greater than 0, and y prime equals k times y for some constant k. Okay, I'm not going to write the next part because I want you guys to tell me what the answer is. Think about what this statement means. And I really want you to think, because I wouldn't doubt if most of you in here could figure this out. This statement is saying the derivative of y is equal to y multiplied by some constant. You've got to think of a function whose derivative is itself, pretty much. That's what this is saying. Isn't that what this is saying? Its derivative is itself? Don't you guys know a function that's the derivative is itself? So then y equals c e to the kt.
It's purge.
It is, pretty much. Well, k has to be up here because when you take the derivative of this, it's a chain rule, so the k is brought down in front. Anyway.
I don't like it.
So here's how you use it. The rate of change of y is proportional to y when t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? Now, this first phrase right here, if it just says proportional, it's implied that it's directly proportional. So they're not going to use the phrase directly. If they're going to use the other one, it would be expressly stated as inversely proportional. So the rate of change of y is proportional to what? You've got to translate that English phrase into a mathematical phrase. What's the rate of change, first of all? dy, but with respect to t. So this first phrase right there, the rate of change, that's dy dt. It's proportional to y, but it's directly proportional. So is it k times y or k over y?
K times y.
K times y.
So is it then when you turn it into the y equals c?
So if this is true, then this also must be true. If this is true, then this is true. Then y equals c e to the kt. That's the theorem we just talked about.
Okay. I can roll with that.
Now here's the one unfortunate thing about these problems. Solving the differential equation is easy. But coming up with the value of c isn't quite so simple, because take a look at how many unknowns we have in just this one equation.
5.
We don't know c, we don't know k, we don't know t, we don't know e, we don't know y. That's why they had to give us so many initial conditions.
I mean, we do know e.
Okay?
Yeah, we know a lot of
So, when t equals 0, y equals 2, that means that 2 is equal to c e to the k
2 equals
times 0.
which gives us all we need to know to find c.
Yeah.
In this case, it really does. I don't know why they gave us two pieces of information. Well, let's see. What's k times 0?
1. I mean,
E.
0.
1 is the answer to the next question. What's e to the 0?
1.
1. So this tells us that c equals 2.
There we go.
Well, the reason they gave us another piece of information is we also don't know k. So let's use the other piece of information plus our value of c to see if we can find the value of k. So now let's use when y equals 4, we know that c equals 2, and now t equals 2. I plugged in a 4 for y, I plugged in a 2 for t, and then I plugged in a 2 for c. This leaves us an equation with only one unknown.
You can divide 2 from both sides.
Divide by 2, I'm going to get 2 equals e
Then we go
to the
ln
2k.
natural log. Equals k times 2 divide by 2, so it's the natural log of 2.
If we're solving for k and it's an exponent, that's no good. You can't solve a variable when it's an exponent. So natural log both sides. So k is equal to the natural log of 2 divided by 2. Natural log cancels the e. So then it's just ln of 2 equals 2k. And then just divide by 2. So now we have our model. The model is y equals 2e to the natural log of 2 over 2 times t.
That's our answer.
No, not quite. Let's go back to some terminology that you guys need to be familiar with. This is a solution to the differential equation, but would you call this a general or a particular?
General.
This is a general solution, right? Because we had some unknowns in there, but by using some initial conditions, we came up with this. What would you call this?
That is particular.
This is a particular solution. We needed the particular solution because they had one more final question. What is the value of y when t equals 3? We could only answer that by figuring out the values of c and k, so that we had only one unknown. You follow? So plug in a t equals 3. That'll give you the value of y. So y equals 2e to the natural log of 2 over 2 times 3. And this is most definitely a calculator problem. So I'm going to first figure out what that exponent is. Natural log of 2 divided by 2. Multiply that by 3. Now you raise e to that power. And then you multiply that by 2. Notice it was really important that you don't round until the very end. If you started rounding up towards the beginning of the problem, then the final result would have been much further off. Okay?
Yes, Dave Summers, attendance for checkout.
Yes, please, take him away.
I'm going to the orthodontist.
5.66.
Hey Gabe, ask your orthodontist if the rate of change of y is proportional to, or the rate of change of y is proportional to y.
I will.
When t equals 2 and y equals 4, what is the value of y
I'll ask
when
you
t
to